Our next guest will discuss research methods for biopolymers and the use of bio-based non-wovens. In her lecture, Mrs. Schippers will examine how the mechanical properties of PLA change and through examples and tests show us what an enormous influence the manufacturing conditions of PLA have on the resulting properties. We welcome Christina Schippers from the German Textile Research Center Northwest in Krefeld. She is a research associate and currently working on interfacial phenomena and physical technology. She will address the topic toward bio-based filter media, assessment of the durability of polylactide fibers under application conditions.
My name is Christina Schippers from
the DTNW in Krefeld, the German Textile Research Center in Krefeld. I'm a research assistant, and today I'm going to say something about the stability of PLA fibers under application conditions. Before presenting the results, please allow me to introduce our institute to you. We are split up into two different fields. First of all, there is the Testing and Assessment Center, an accredited laboratory, and the Research and Development Center. And this development center is divided into 4 research groups, and every research group has a different focus. I'm working together with Larissa Zarkova, examining interfacial phenomena and physical technology. Others, Klaus Obwist, deal with environmental technology or green chemistry and nanotechnology. Thomas Meyer is heading this project. Basically, it's chemists working in our industry. That is why we focus on chemical aspects, analysis, fitting of textiles. And these textiles are delivered by our project partners. This may be companies or research institutes. And very often these projects are done in close collaboration with other research institutes so that we get a lot of different experiences and use a lot of different expertise. So that in the end we have broad or wide results available. Some examples for cooperation partners are the STFI in Chemnitz or the IUTA in Duisburg, which very often helps us with filter tests. The results I'm going to present to you today are coming from the project BioFilter. This is an IGF project which was terminated by the end of 2020. Motivation is that we want to use nonwovens made of petrol-based synthetic fibers or glass fibers. Filter media, the biggest challenge is the price-performance ratio, and especially filter media by different materials. Material costs play a very important role, and they make up a very big proportion of the costs. That is why it is difficult to use polymers which have a higher purchase price. That is why we have to optimize the performance so that the high price is justified in the end. And in the example of biopolymers, of course, it is an ecological aspects, the same efficiency of the material. Aim of the project is to use filter media from bio-based fibers, very often PLA. For that reason, we have PLA monofilaments, which are homogeneous, so you can carry out good measurements. We know from many biopolymers or PLAs that production conditions do influence the characteristics or properties, especially temperature, for instance. If you increase it in the device, so polymer might degrade, or stretching relations, crystallinity may be increased. So these are influencing parameters which can be influenced by manufacturing alone. Talking about filter materials, we processed different materials, looking at different properties, filter testing, but this was carried out by STFI, and that is why I do not want to tackle on this. The PLA we use comes from an American company. We deliver it to Monofil in Hennef. It is an industrial partner. That is why we can use an industrial facility, so we can reach different properties than described in literature or by other research institutes, because simply we can use a bigger device with different temperature flows. On the other hand, it's lab scale only. Nevertheless, we face the problem that hydrolysis resistance of biopolymers is quite bad. Saying bad, that's to say, we know that degradation is possible only by that, but with filter media, the degradation of polymers plays a subordinated role, because by loading the filter medium, it has to be burnt anyway. So we want to have biopolymers, we want to use it because they are ecologically friendly, with a high hydrolysis resistance, so that they can be applied under high temperatures. There is no standard measurement to test the properties, so that's why we came up with an own method, artificial aging and characterization by DSC measurements and tensile tests, as well as relaxation tests. The measures may be a bit difficult to translate. We are chemists and we look at it from a chemical point of view. However, the results from these tests can be explained quite easily. So that is why I do not want to talk about the background, but I would like to focus on the result. We also published an article about the results, and if you are interested, you can read chemical aspects in this publication, or I'm also happy to answer your questions after my presentation. Let's start with the results. Let's start with a comparison between the granulate, which we got from Networks, and the non-treated monofil. As I said, by processing, the polymer is degraded, so that is why we have a lower melting temperature, which you can see here in the second picture. In the lower picture, what happens with stretching relation, we have a crystallization peak, the lower temperature compared to the granulate, and this is due to the stretching relaxation. So by these molecules, we can reach an easy crystallization, resulting in better material properties. That's to say, it's more stable than amorphous polymers. At the same time, it is interesting to look at the temperature. Normally, if you have a lower melting temperature, then you have a lower temperature resistant material. We have a transition point of 71 degrees Celsius. This is above the value NatureWorks indicated in a data sheet. Despite reduced mole mass, we have a higher field of application. And this field of application is normally limited by the glass transition temperature. And this is the maximum temperature we use for our artificial aging test. We said we will use up to 70 degrees Celsius with different humidities in order to cover a broad range where we can carry out artificial aging. And the results are here: 60 degrees Celsius, artificial aging at 60 degrees Celsius, relative humidity ranging from 20 to 90%, and an aging duration of 2 weeks. Looking at the classical tensile testing, it's quite easy to interpret this. We have high elongation, decreasing material strength for high elongation, but marginal changes in elastic area. If this material is used, we don't have stress of 20, 30 or 40%, but we stay, as I said, in the elastic area there where the material is used, and this is the lower diagram. Here up to 2%, you see it a bit enlarged. I think you can rather estimate than really see the differences, but unfortunately these curves can't show the differences. Just to show it a bit better, we did relaxation measurements. With the relaxation, the material is stretched by a certain value and kept for several minutes. So with a stretch of 1.5%, the area around the stretching can be defined, and these are the results I'm showing here. Upper part, you see just the measurements, and just to give a broader insight, we developed an own model about the lifespan forecast. The models, the formula is here calculation number 1. I would like to talk about this model, but I think it is too detailed. If you are interested, please refer to the publication or ask questions after my presentation. After mechanical measurements, of course, we did thermal properties, and the results prove what we learned from the testing of the mechanical properties. So 85 degrees Celsius in the upper diagram, there is a just relaxation peak, as you can see, and this decreases with increased humidity. It's a familiar phenomenon we just observed before, and in addition, the melting temperature can be observed at high limits. For the relative humidity, it is decreased. Here, it is probably not very good to spot. We have a decrease of 1 degree Celsius, but with some measurements, GPC measurements, it's just to assess the mole mass of the polymer. This proved that by reduction of the melting point, or by 1 degree, we have a reduction of the mole mass. So with this extreme humidity, 80%, the polymer will be degraded. We tried to measure the diameter in order to say something about the shrinking behavior. You see it in the lower diagram. We see standard deviations. However, you can see a trend. First of all, the polymer or the fiber shrinks up to 65% RH, and up 80% it is relatively constant. So there is no change. This is the limit we also observed between 65 and 80%. Something happened, so we say up to 60%, 65% stable material can be used under these conditions, and starting at 80, it is degraded. It's not hydrolysis resistant at this temperature humidity combination. We carried out some further tests, not only 60 degrees, but 50 degrees and 70 degrees Celsius. Here it is very interesting to see that this limit between 65 and 80% could be shifted by increasing temperature. By increasing temperature, this limit decreases to 20 to 50%, and if temperature decreases, there is no limit any longer. So up to 50 degree, 95%, the material is hydrolysis resistant. Here only the DSC measurements can be read. Of course, you can prove it by mechanical testing, but DSC measurements are best to assess looking at melting temperatures. For the 70 degree, you see a reduction, 10 degree reduction, 5 to 10 degree reduction, but thinking about reducing the melting point to 5 to 10 degree, then it is a degraded test, and it looks like this. So these were the samples from this climate box. So it was degraded completely. So if we decrease the melting point by 10 degrees, there is hardly any polymer left. So this difference, 1 to 2 degrees Celsius, is significant in order to change the properties. It is enough to describe hydrolysis. To summarize, we can say that we looked at different methods to describe the hydrolysis of PLA fibers, and by applying these methods we could differentiate stable and unstable tests. So we set temperatures and humidity. On the right-hand side you see a summary of the stable samples. If you want to use another diagrams, looking at temperature and humidity, relative humidity, you see that these open circles are the degraded tests. Looking at the absolute humidity, it is even more interesting because we see a kind of threshold value. So the threshold value, which normally is temperature dependent with relative humidity, it's now independent of temperature because the humidity includes temperature, and as a threshold limit here in our case we can state 90 gram per cubic meter. That's to say the PLA we artificially aged in manufacturing with the aging time is to a humidity of 90 gram per cubic meter stable.
Das nochmal darzustellen, ist es wichtig, dass ich das betone.
It is very important to underline it, especially it's very important for me. The differences we found are marginal. I mentioned the example of the melting point. I talked about 1 degree, you see something, 10 degree, you see significant differences, and these are the respective diagrams. Looking at the degraded samples, I showed the stable samples, so all the lines are above the original and unstable is below the original. So this differentiation is significant. The target of this project, of course, was nonwovens. I did not talk about this, and this is what makes this test a bit problematic, because these small differences I mentioned, which are important nonetheless, can't be used with nonwovens because they show irregularities, especially when our partner SCFE produces them at technical plants. These stretch tests of standard deviations are hardly possible. So that is why we have different ways how to further develop our research. First of all, we could continue with PLA monofilaments, so try to get results out of that, or we try to translate the data to nonwovens, whereas we know or we assume that it's not possible with mechanical assessments. We tested it, it might be possible, but we said, well, there might be better possibilities, and we tried to use filters for testing because we want to produce filter media. That is why we can generate data by using and applying the filters. And here we had pre-aged samples and assessed it, looked at the filter performance, and you can see here very well what we found with the monofilaments already. With under extreme conditions, 70 degree, the filter performance decreases. Under mild conditions, here 50 degree Celsius, 50% humidity, then the filter performance is relatively stable. So this corresponds with our expectations when we translated our method. The problem, however, is, and you can see it in the next step, if we did not age it before the filter test, but during the filter test, then there is another influence, namely the flow which goes through the nonwoven, and this flow seems to have such a high influence that even at 50 degree and 50%, where the sample was stable beforehand, here we see a reduced filter performance. So we thought there will be a pre-aging, there will be a test of the filter performance, and then we have results. Unfortunately, it turned out not to be realistic. So we had to think about different kinds of measurements in order to understand the special characteristics, to research these special characteristics. So you cannot translate one result to the other, because materials seem to behave in a very individual way. Especially around these topics, we want to realize other projects together with our partners. They have a lot of expertise with nonwovens, they work with PLA. If you are interested in these things, improve characteristics of PLA or application application of bio-based nonwovens, please do not hesitate to contact us, contact me, or contact my colleague Larissa Zarkova or Mr. Taubner from the STFI. Thank you very much for listening. I would like to say thank you to our supporters and sponsors. And if there are any questions, I'm pleased to answer it.
Thank you very much for the exciting information and the insights, which was very precise, and a very warm welcome to Christina Schippers. Hello.
Hello.
Thank you.
Thank you. We would like to start a discussion, and my colleague already received some questions which he would like to pass on to you. So we would be happy if you would answer them.
Yeah, thank you.
Great.
First question from my side, because you were telling about the influence of the flow through the filter media having an impact. Can you disclose what kind of media was flown through the filter?
Just air.
Air.
Nothing else.
No, nothing else.
Air. It was just a filter test without any particles or anything like this.
Curious. Okay, crazy. I was not expecting that, to be honest.
We either.
Yeah, I've seen that. Very interesting. So looking really forward how this goes on. From the audience, we have a question. Which kind of filters are the PLA filaments used for? Is there a specific application? Is it really for filtering the air or also for other medias?
Yeah, the problem is the application condition. So we have to find an application where we are close to room temperature. Mm-hmm. So high efficient filter are just not possible because it degrades at 60 degrees. So yeah, in general, we try to use it as room filter.
Can you also compare the hydrolysis stability of the PLA filaments in comparison to other materials? So, for example, polyamide or some other hydrolyzing materials. Is there a range that you can give?
We have no measurements about that. I'm sorry. We are so busy with the PLA that we had no time to analyze other materials. But we try to use blends. So we also analyze a PLA PBS blend. And that was interesting to see. We had worse hydrolysis resistance and was kind of fibrillation. So we don't have a mixture between PLA and PBS. They're just not easy, like fibers in the monofilament, which are laying next to each other. And the hydrolysis reduces the contact between the two fibers in the monofilament. So we have less hydrolysis resistance. That was something really interesting we saw. And we want to go on with this work as well.
Mm-hmm. Yeah, very interesting. I mean, we've also seen some of the work of Mitsubishi, so of PTT MCC, in the previous presentation, also for that staple fibers. Very interesting. I think there's a lot of ongoing interest and R&D ongoing in this area.
Yep.
I think that's very interesting to follow. To thank you for your contribution and
welcome.
Send our warm regards to Krefeld, and hopefully we'll meet each other in person for the next event.
Yeah.
I hope so. Thank you.
Thank you very much. Have a nice day. Bye.
Bye.